Today we're going to take a look at quadratic functions, and we have dealt with quadratic functions and solving them before, but we're going to take a more graphical approach in terms of what these functions look like when they have when we look at their specific components when they're graphed. So to start with, the standard form of a parabola is actually written in much the same form that we've been looking at when we looked at transformations of functions. The standard form is y equals a x minus h squared plus k. So a few details of this form. You'll notice that there is an h here, it's the opposite sign, and a k here from what we've identified over here as the vertex. Visually speaking, the vertex is this location down here, and you can ignore sort of the gridding marks. I just wanted a basic one here so you could see it. It's either the lowest point, or if this were flipped upside down, it would be the highest point on the graph. Okay, that's called the vertex. If you have an a value that is positive, then the graph will open upward, and that's what we see happening on this particular graph. If the a value had been negative, this graph would be flipped upside down and it would be opening downward. If the a value is large, in particular by large I mean bigger than 1, you actually have what we would call a narrow graph. It's going to look kind of skinny. And then if the graph's a value were larger, or between 0 and 1, we would end up with a wider opening graph. And then the last thing is, and I'll mark this sort of dotted on my grid, we have the axis of symmetry, and this would be the vertical axis. It's a vertical line that would, you could either think of it as splitting your graph in half or splitting it sort of where it would fold to be symmetric on both sides. That's why it's called the axis of symmetry. On this graph, this would be my axis of symmetry. You can see how it splits the graph in half, or if you fold it along this, you'd have the same image on both sides. All right, so we're going to take basically a graph, much like the one we just did, and we're going to talk about these features. So if you take a look at this graph, we would say that this graph is opening down. Now, we're not going to identify the actual components, but that means the a value would have been negative. The vertex on this one is actually a peak or a high point or maximum on this graph. And the vertex, you can see, looking at the x and the y components, is the ordered pair 3, negative 2. Oops, I put that in the wrong spot. Let me move that up. 3, negative 2. Intercepts. Intercepts is locations where it crosses the x or the y axis. So it actually doesn't cross the x-axis. It could have, right? If this whole thing were shifted up a little bit more, we could have up to 2 places where it actually crosses the x-axis and we'd have x-intercepts. This one doesn't, but it does have a y-intercept, this location right here. And at least in terms of what it visually sort of appears to be, it looks like it's crossing at negative 6. So this is the point 0, negative 6. And on this one, that's the only intercept. And then the axis of symmetry, that is the location where it cuts the graph in half, always goes through the vertex. And this equation is the line x equals 3. Because at every point along that line, the x value is 3. The next thing we're going to do is we're going to actually take an equation and we're going to graph it. So we're going to identify some of these key features that we've been discussing in order to do the graph. So the first important feature is the vertex. The vertex is in those locations, where the negative 1 is and the negative 4. It's always the opposite sign of what happens inside with x, so that would be 1. And then it's the same sign as what happens outside, so negative 4. So my vertex is positive 1 and negative 4, which would be here. The next thing to notice is that the a value equals 3. The first issue is that that means it opens up. The second thing to notice is that that means it's going to be narrow, and in particular it allows us to plot the points where we're going to get our next ordered pairs on our graph. And we talked about this back when we did transformation of functions, is that normally on a parabola we would go up 1, right 1, up 1, left 1. Or if it were negative, we would go down 1, right 1, down 1, left 1. But this value is 3, so we go up 3, right 1. And, oops, I didn't get that right. Here we go. And up 3, left 1. And so these would be on my graph. And of course it's up because it's positive. And then the u value, or the u shape, right, because it's a parabola, is how we would open the graph. So it should look like a U. Mine's not super U-like. My graph's a little bit sketchy, but it should look like a U. So just pretend for a moment with me. And that's really nice because this one was given to us in standard form. But what if we're given something like this? How do we deal with this equation that is not in standard form? Well, we actually use a process that we've used before, but we've used it, of course, for a different reason. We used the process called completing the square. So let me show you how it works in this context. All right, so what we're going to do is we're going to separate these two pieces, the pieces with x in it, from the piece that does not have x in it. Any coefficient on x squared has to be factored out, and in fact we see that happening right here. So x squared is what's left. If we factored a -3 out of the positive 12, we would have -4x. And then we're going to leave a blank spot and put that -9 on the end. Right in here, we need to complete the square, and we do that by taking this -4, the linear term, we divide by 2, that gives us -2, and then we square it. So that would give us a +4. Now, the kicker is that 4 is not really 4. It's actually, let me delete that. There we go. It's actually 4 times -3. Because this 4 and this -3 are multiplied together because one's inside of the parenthesis and the other one is factored out of it on the outside. So this really means that I subtracted 12 from my equation. So to compensate, I must also add 12, right? If I subtract 12, I have to add 12. And then the last thing we need to do from an equation standpoint is to clean it up and factor. So in the middle, this factors, of course, as a perfect square. That's why we did it. So it's x minus 2 squared. And then -9 plus 12 is actually +3. So my vertex, now I'm finally at the point like I was on the last problem. My vertex right here would be 2, 3. Remember, it's the opposite sign of what's on the inside. And then my amplitude being -3 means it's going to open down and be narrow. So 2, 3 would be right here. And then a amplitude of -3 means we go down 3 and left 1. Oops. And down 3 and right 1. So these are my secondary points that I will then connect in a smooth U shape to look something like that. So there's a lot more work on the front end of this one, getting it to be in the standard form. Okay, so in addition to finding the vertex, maybe the axis of symmetry or the amplitude, we also would like sometimes to find the zeros. So the word zeros here actually means x-intercepts. Okay, and an x-intercept likewise means the places where y equals 0 or where it crosses the x-axis, those equivalent phrases. Hang on. There we are. Okay, so if the x-intercept means that y equals 0, then I can actually let y equal 0 in my equation. And from this standpoint, if I can factor, fabulous. If I need the quadratic formula, I can use that. Have lots of choices. I could even complete the square, although that's probably not the first one we usually think of. This one actually does factor. It factors very nicely. It's x minus 9 and x minus 9. And since they match, if I set either one of them, of course, equal to 0, I get the same value, and x is going to be 9. So my x-intercept, or my 0, means the same thing, is x equal 9 and y equal 0. Now, as you're aware, not all functions, as we said, factor, and there's actually a really nice way to handle this using your calculator. So if you have a graphing calculator, you can do the next step on that. If you don't have one, I would encourage you to borrow one when we get to the test, because there definitely could be some questions about graphing in this perspective. For now, if you don't have access to one readily, you're welcome to use an online graphing program to get this component. So using your graphing calculator, if you have a TI 83 or 84, that's kind of my reference point of what I'm going to be using. What we're actually looking for, again, is where it crosses the x-axis, right? And this one, as you can tell, would not be super friendly to factor out that -9 from the -24. So doing this as completing the square would be messy. We could use a quadratic equation, right? If we wanted to use this as a quadratic formula, that would be a possibility. This one actually happens to factor, though not all will. So if we were to graph this and we were to put this into y1 on our calculator, so this says y1 equals all of this, and we were to look for our x-intercepts, we would actually see a graph where it looks like it's sort of bouncing off of the graph at a value on the left-hand side, barely on the left-hand side. Actually, I'm going to continue that and I'll just shift it down since I have that capability. Okay, roughly speaking like that. It kind of looks like it's bouncing here, like it just touches and it bounces right back off. There's a lovely feature in your calculator that's called the, you can zoom in and you can try to get really close to this. That's really tough. But there's a feature called the minimize or maximize feature. So this one's a minimum. There's also a feature called the zeros feature. And that's actually the one we want here because it looks like it's the minimum, right? But it's really hard to tell even when we zoom in if it's not maybe crossing or going across. So the zeros feature is really nice. It tells you what the x-intercepts are, namely the zeros. And the way that you do that is you plug your equation, of course, into y1, like I said. And then if you hit second calc, there's a button that says second, and then there is a feature, it's actually the trace button, which is calc. If it's in yellow or another color above it, it's the calc menu. So you hit second trace, and there's an option number 2 that says 0. This is a really good thing that if you're not sure how to do this with your calculator, our tutors in the Success Center are very competent with their calculation to be able to help you with this. So this is the 0 feature. And if you select the 0 feature, it asks you some questions. It asks you left bound. It asks you, and if you enter a number, it's going to then ask you for the right bound. And after we enter that, we're going to be asked for a guess. Okay, so left boundness means you need to be to the left-hand side. So you simply arrow to the left until you're for sure, to the left of the 0, and you press enter. And once you do this, this prompt for right bound comes up. And when it says right bound, you arrow to make sure you're to the right of the intercept, and you press enter. And then when it says guess, you just get pretty close to where the actual value is, and you hit enter. And when you do that on this particular one, it's going to give you an x value that says -1.33333. It might even eventually at the end round us off to 4 or something like that, but it does this. So for the purposes of what we're doing with the graphing calculator, I'm okay if you just write that this is -1.3 repeating. And then, it's the ordered pair if you would wish, but this is just asking for the zeros, right? What x value does it equal 0 at? So this would be our answer. If you feel uncomfortable with that notation, you can change it into notation that's actually fractional form. That's -4/3. We'd also like to be able to know what the zeros are and go backwards and find the functions, if you will. So we're going to take a couple of examples of that. We're given what the x-intercepts or the zeros are, and we're asked to find the function that corresponds to that. And so you'll notice this really lovely relationship, say for instance over here, between the the factor, which is what I want to say, and the intercept, is that what we end up having is that they're just the same thing basically, but the -9 or the 9 is moved to the left-hand side. So if x is equal to 9, then x minus 9 is the factor. And so over here, if x is equal to 4, then that means that x minus 4 is a factor. And if x is equal to 5, then x minus 5 is a factor. So when I'm writing my equation y equals, it will have an x minus 4 in it, and it will have an x minus 5 in it. And that's all I can have in order to have a quadratic, so I'm done and I just multiply this out. So this would give me x squared minus 9x plus 20. Now the second one is a little bit different because it tells you the only zero is x equal negative 10. So that means, of course, that x plus 10 is a factor, but I can't just have y equals and x plus 10. That's not quadratic. But what I could have is I could have more than one x plus 10. And in fact, I need two of these factors in order to actually have a quadratic, so that's exactly what I need. And if I multiply it out, I have x squared plus 20x plus 100. And what this would do visually is that this one is crossing through the x-axis. So it looks something like this, whereas this one is bouncing off of the x-axis, so it looks something like that. I'll move it down to touch like that. It just bounces off, it barely touches it. All right, so let's actually take an example of one where we have a function again and find the x-intercepts and the vertex. So we find those in different ways. Of course, we said before that x-intercept is when y equals 0. So if I let y equal to 0, I have x squared minus 8x plus 12. We love to factor if we can, right? That's the simplest way to solve it. Quadratic formula is maybe our second choice. Both of these are x, and they're both subtraction because the sign at the end is addition, middle sign is subtraction. I need two numbers that multiply to 12, but add to 8. So that would be 6 and 2. So my x-intercepts would then be where these equations are solved for 0. So x equals 6, x minus 6 equals 0, x minus 2 equals 0, which gives me x equals 6 and x equals 2. Now, and when I'm asked specifically for zeros, I could leave it here and that would be fine. But this one says x-intercepts, and intercepts are points. So this is negative 6, 0. Not negative 6, positive. Positive 6, 0, and 2, 0. So these would be my x-intercepts. But it also asks me for the vertex, and in order to get the vertex, there's a couple of ways to do it. We're going to focus on completing the square because it works in all scenarios for all types of questions that were asked. So we're going to take y equals x squared minus 8x, and we'll leave a blank spot, and then minus my 12 out at the end. And to complete the square, I take my middle term, negative 8, divide by 2 gives me negative 4, and then squaring, that gives me positive 16. 4 squared 16. Because there's no sign on the outside like there was in my earlier problem, I really did add 16. So to compensate, I subtract 16, and I realize I had a sign error. That should have said a plus 12 to begin with. Okay, factoring this, I have x minus 4 squared, and then minus positive 12 and minus 16 at the end give me a negative 4 at the end. So I have x minus 4 squared minus 4. Then the vertex is very nicely found by identifying it from the components of the addition or subtraction going on. Opposite sign of the part by x, so it's 4. Same sign from the value at the end, so my vertex is 4, negative 4. Similar question, we're going to do the same thing, but identify it from a graph. And so you're looking for the same things. Graphing calculator, find x-intercepts and vertex. So the x-intercepts, of course, is when y equals 0, so where it crosses the x-axis. So if I graph this and I put in y1 equals 2x squared plus 2x and minus 5, I can use again that 0 function. Remember the way I get 0 is I hit second, trace, and I choose option number 2. It asks me for a left bound, it asks me for a right bound, and a guess. And on this one, it doesn't just bounce off the x-axis like the previous one did. It actually cuts through. And when I look for them, I find that there are 2 zeros. We will use approximations with 2 decimal points, and this happens at negative 2.16, and then at positive 1.16. Those being 1/6 is not always the case, right? But it is on this one. So my x-intercepts would actually be at negative 2.160 and at 1.160. Now finding the vertex, you can still put it in your calculator, right? Same way as you did before at y1. But you're actually using a different function. You have to decide if this is a minimum or maximum. Because the a value here is a positive 2, the a value being positive means that it's going to open up, which means I'm looking for a minimum. So if you're in that same menu, second trace, you'll see option number 3 says minimum, right? So if you select that option, it asks you again, left bound, right bound, guess. Just like the other one did, works exactly the same way. So you need to make sure you're on the left-hand side of the minimum and press enter. Arrow to the right-hand side of the minimum for right bound and press enter. Guess just means that you're close to the value and you press enter. And it will end up giving you this ordered pair on this one, negative 0.5, 5.5. And that would be the vertex for this particular quadratic equation.